Hello students, in the last session we have seen about effects of condenser and evaporator pressure on COP. The theory we have discussed in our last session. In this session we will see few numerical problems on the same heading, effects of condenser and evaporator pressure on COP. Very simple problems we will discuss, and you will understand the effects of the condenser and evaporator pressure on COP very easily. We will give its inference after solving the problem. So far we have seen all these topics. In last class we have seen its theory, condenser evaporator pressure theory. In this session we will see very simple problems on the same heading. So we will see the first problem. A vapor compression refrigeration system, in short it is called as VCRS, uses R134A. So refrigerant type is R134A, and we have seen what are the different types of refrigerants in our earlier unit. And with this clue we have to find the enthalpies from refrigeration tables for this particular refrigerant. As the refrigerant, the system operates between the following conditions. So there are two cases are given here. Evaporator pressure is 200 kPa. So evaporator pressure is 200 kPa, that is first case. In second case, evaporator pressure is 250 kPa, and the condenser pressure is PC, that is 900 kPa. So the enthalpies at key points from refrigerant table we have to find this. H1 for case 1 it is PE, that is the evaporator pressure 200 kPa and evaporator pressure 250 kPa. For H1 is nothing but enthalpy at compressor inlet, so that is 250 kilojoules per kg, and for second case it is 260 kilojoules per kg, and H2 enthalpy at compressor outlet, that is 290 kilojoules per kg and 300 kilojoules per kg for second case, and 300 that is H3 enthalpy at condenser outlet 110 kilojoules per kg for case 1, and same 110 kilojoules per kg for case 2, and similarly for H4 enthalpy at expansion valve, throttling valve, in terms of kilojoules per kg, same, that is 110 kilojoules per kg for both the cases, case 1 as well as case 2. So the solution is very simple, very easily you can solve this. We have to find the refrigeration effect first with the given with available enthalpies. So first we have to calculate the refrigeration effect, RE equal to H1 minus H4. So for case 1 it is 140 kilojoules per kg. So we know H1 and H4 from refrigeration table, we found it for the given refrigerant. And for case 2 it is 150 kilojoules per kg. So work done by the compressor W equal to H2 minus H1. So same, we know H2 as well as H1, and W1 equal to 290 minus 250, it becomes 40 kilojoules per kg, and for case 2 300 minus 260, it is also 40 kilojoules per kg. And we have to find the COP next. So COP we can found from RE divided by W, that is H1 minus H4 divided by H2 minus H1. So that is equal to 140 divided by 40 equal to 3.5, and 150 divided by 40, that is equal to 3.75 for case 2. So that is COP 2. So now we can conclude like this. With this COP1 and COP2, increasing evaporator pressure from 200 kPa to 250 kPa, the COP is also getting improved, that is 3.5 to 3.75. So it is a desirable what you call operation here. So evaporator pressure on increasing, we are getting better COP, and this is because higher evaporator pressure increases the refrigeration effect without increasing work input. So without increasing work input, we are getting better refrigeration effect. So this is the conclusion from this problem. So increasing from 200 to 250 kPa, it gives a desirable COP. We will see another problem. So problem 2, the refrigeration system operates between condenser pressure PC 900 kPa and condenser pressure PC is 1100 kPa. So here in the earlier case we have seen the evaporator pressure effect. Here we are going to see the condenser pressure effect. So here PE is 250 kPa, that is the constant here, and from enthalpy, that is refrigeration table, and H1 is given. So here this table is given in the problem itself. If it is not given, then we have to refer the refrigeration table. So, see, in this problem there is no refrigerant given. What type of refrigerant is unknown. If it is unknown, they will give these details. Once you get these details, you can solve this very easily. So H1 compressor inlet kilojoules per kg, for PC 900 kPa it is 260, and for 1100 also it is 260 kilojoules per kg, and H2 enthalpy at the compressor outlet kilojoules per kg 300 and 320. H3 is condenser outlet, it is 110 and 110, it is same, and H4 is also same. H4 is also remains same, it is 110 kilojoules per kg. So first, in like earlier problem, we have to calculate the refrigeration effect first. So Re equal to 260 minus 110, it is 150 kilojoules per kg, and Re2 for second case it is 260 minus 110, it is also 150 kilojoules per kg. Calculate the work done by the compressor. W is equal to W1 equal to 300 minus 260, that is 40 kilojoules per kg. W2 equal to 320 minus 260, so that is 60 kilojoules per kg. So then we can calculate the COP. COP equal to RE by W. So RE1 by W1, 150 by 40, it is equal to 3.75, and case 2 COP2 equal to 150 by 60, it is equal to 2.5. So from here we can conclude like this: increasing condenser pressure from 900 to 1100, the COP is getting decreased, so it is not a desirable one, and COP is reduced from 3.75 to 2.5. So this is not a good sign, and we have to keep the minimum pressure, condenser pressure. This is because higher condenser pressure increases the compressor work and reducing the efficiency. So compressor work is getting increased. So here W2 is more than W1. So by increasing the condenser pressure, the compressor pressure is getting increased. So the compressor work is getting increased. So that is the conclusion here, and you can see here this is the key takeaways, and parameter is given here, and effect of COP, and increases evaporator pressure, it is good, and COP is increases, and decreases COP evaporator pressure, COP is getting decreased. Increasing condenser pressure, COP decreases, and decreasing condenser pressure, COP increases. So this is the inference from these two problems, students, and we will see one more problem where we can combine both the effects, and we will conclude this. Effect of condenser and evaporator pressures on COP in an industrial refrigeration system. An industrial ammonia refrigeration plant operates with evaporator pressure is 180 kPa, that is case 1, and 250 kPa for case 2, and then condenser pressure is 1100 kPa for case 1, 950 kPa for case 2. So enthalpies for the two cases, so we know the refrigerant, it is ammonia. So if we know the refrigerant as ammonia, we can take the enthalpies from the refrigeration tables. And the case 1, the H1 at evaporator exit, it is enthalpy is 275 for case 1 and 285 for case 2, and H2 compressor exit 320 kilojoules per kg, and case 2 it is 310, and H3 at condenser exit 120 and 115 respectively. Similarly for H4 expansion valve exit, it is 120 and 115 kilojoules per kg. So now we can solve this very easily. Calculate the refrigeration effect as we did in earlier cases. So here RE1 is H1 minus H4, 275 minus 120. So 275 minus 120, that is 155 kilojoules per kg. For case 2, it is 285 minus 115, 285 minus 115, that is 170 kilojoules per kg. Now we can calculate the work done. Work done by compressor W1 equal to H2 minus H1, so that is 320 minus 275, 45 kilojoules per kg, and for case 2 it is H2 minus H1, 310 minus 285, it becomes 25 kilojoules per kg. So work done here, it is lesser, so W2 is better than W1. So now we have to calculate the COP. So COP1 equal to 155 divided by 45, so that is 3.14. So COP2 is 6.8. So now this is better. COP2 is good, and case 2 has significantly higher COP than that is case 1, and raising the evaporator pressure and lowering the condenser pressure greatly improve performance. So now we can combine both the effects and say the evaporator pressure is rising by increasing evaporator pressure, and by decreasing condenser pressure we will have the best refrigeration effect performance. So industrial ammonia refrigeration plant optimize evaporator and condenser conditions to maximize COP and minimize power consumption. And this is small table inference from this, and system type is two-stage system. Intermediate pressure improves COP, cascade system high PC reduces COP, and industrial refrigeration lower PC and higher evaporator pressure improves COP. So this is the inference that we get from this, and in next session we are going to see the multi-pressure system, where we are going to deal different systems where multiple pressures can be operated, and that we are going to start in next session, students. Now we can stop here, and you can refer this books. This is the very good book for this topic, SCP Aurora. Please refer this book. Apart from this, we have other books, and Kurmi. There is not much information available in this Kurmi book, so you can better rely on Aurora book, CP Aurora. And anyhow, we have these resources also. So we stop here. We will meet again in next session, where we are going to see multi-pressure systems. Thank you, students. We stop here. Thank you.